Welcome to the Deep Dive, where we take a stack of sources and distill them into the most critical insights for you. Today, we are tackling a really persistent challenge in AI, something that's holding back the future of autonomous systems. How do we actually train these incredibly capable language agents using reinforcement learning without it costing a fortune?
Right. And our sources today focus on a new framework that tries to solve this, something called DreamGym.
So our mission is to understand how DreamGym gets around the huge costs and the stability problems you see with traditional RL.
And the core problem is really simple on the surface. To train a large language model agent with standard methods, you just need a staggering amount of real-world interaction data.
Which is just not practical, economically or logistically, especially when you're talking about complex real-world tasks.
That difficulty is the knowledge gap we're here to fill. The old way of doing things using reinforcement learning is hitting a very hard wall, a scalability wall.
So we need to understand why it's so expensive and inefficient before the solution can really make sense.
This deep dive will get into how the researchers address those limits, the expensive data, the lack of diverse tasks, and the really volatile reward signals that hold these agents back.
Okay, let's unpack this. Starting with those fundamental barriers. What makes training these LLM agents so tough?
The sources lay out 4 big bottlenecks. We always hear that AI models are expensive to train, but it's the interaction data, what the agent actually does in an environment. That's where the costs just explode.
So the first one is just that, cost.
High cost and very low sample efficiency. Think about an agent trying to learn how to use a complicated piece of software, like the WebArena benchmark.
Okay.
Real-world tasks involve these long sequences of decisions, and every single step, it costs you. Whether that's CPU time or an API call, it adds up. It makes gathering data incredibly expensive and slow.
And I imagine that inefficiency then gets multiplied by the second problem you mentioned, the lack of diverse tasks.
It does. Most of these environments, especially for complex tasks, they only have a very limited static set of instructions.
So the agent just sees buy this item over and over again.
And its ability to generalize is just crippled. And you can't just easily add more tasks. If you want to create new complex instructions, you need a person, a human expert, to not only write them, but also to check if they're even possible for the agent to do.
So that becomes a human bottleneck. You can't scale the curriculum.
Then you have the third barrier, which is the quality of the signal itself.
You mentioned WebArena, so thinking about any dynamic environment, like a website or an app.
Right. Those settings can give you noisy or sparse, or sometimes just plain false feedback. A button might not load right, or the site says success when the action actually failed. And this kind of unreliable info makes stable learning almost impossible.
And there's a safety aspect to that too, isn't there?
A huge one. That instability gets worse when you think about safety. In a real environment, an agent could do something irreversible, like confirm a purchase or delete a file. There's no reliable undo button.
So the risk is just too high, and the feedback loop is too messy for the kind of high-volume training RL needs.
And the final piece of the puzzle is the infrastructure challenge. The engineering complexity.
The systems themselves.
Yeah, these platforms are all built on different kind of heavy-duty backends, often using things like Docker or virtual machines just to handle all the dependencies.
Which must make it a real headache to do large batch rollouts.
It's an engineering nightmare. You have all this computational overhead just to manage resetting the environment. That's the opposite of what you want for a general-purpose scalable system.
So you're stuck, you're trying to build a generalist agent, but you're caught between these massive costs and just unreliable, limited data. But the research offers a really foundational insight here, and it's what DreamGym is built on. They argue that you don't need a perfect pixel-for-pixel clone of a real environment.
No. Instead, they say LLM agents just need interaction data. That is, and this is their phrase, sufficiently diverse, informative, and causally grounded.
That's a huge shift in perspective.
It really is. It moves the problem away from engineering, building a perfect expensive simulation, and reframes it as a problem of representation.
So if you can just represent the core dynamics of the environment in a lightweight, information-rich way, then you can scale.
And that's exactly what experience synthesis is all about.
Which brings us to DreamGym. It's a unified framework that completely changes the training loop. Its core idea is not to use those expensive real-world rollouts,
but to synthesize diverse experience data and to do it in an online, adaptive way.
How does it do that?
It does it by distilling the environment's dynamics into what they call a reasoning experience model, or MEX.
MEX.
And MEX abstracts the whole environment into a discrete textual space. This is the key. Instead of trying to recreate messy HTML or complex 3D graphics, MEX generates the core experience as structured text.
Hold on, if MEXP is only working with abstract text, aren't you running a huge risk of a sim-to-real gap? I mean, how can an agent trained on clean tokens handle a real messy website with pop-ups and loading errors?
That is the essential question. And the answer lies in the efficiency gain. The researchers found that for language agents, the most important information is the causal chain of events. The action and the resulting state change, not the visual details.
So it doesn't need to see the button, it just needs to know the button exists and what happens when it's clicked.
Right. Instead of simulating all the raw HTML for a shopping site, MEX just synthesizes a clean, token-efficient list. Product A is available, price is $10. This huge reduction in irrelevant data makes training MEX super sample efficient. It lets the agent focus on the cognitive steps it needs to learn. What's fascinating here is the shift from replicating raw physics or pixels to synthesizing experience in an abstract, meta-representational textual space. It just simplifies everything.
Okay, so that brings us to the mechanics of the framework. It has these three interlocking pillars that make it all work. Let's start with MEX inference. How does this model actually generate the data? MEX uses chain-of-thought reasoning to predict the next state, what the environment will look like after an action, and the reward. This is important, right? It's not just guessing.
No, it's showing its work. It uses that reasoning to logically figure out the next step and make sure the state transitions are consistent. That step is critical for reducing hallucinations, factual errors in the synthetic data.
And it doesn't make that prediction in a vacuum.
It doesn't. It's conditioned on three things. The interaction history so far, the specific task it was given.
Yeah.
This is clever. The top few most similar successful examples it can find in its replay buffer.
So it's using a mix of its own history, the current goal, and past successes to guide the synthesis.
And for the reward, the scheme is sparse, but it's very clear. The model gets a reward of 1 only at the very final step, when the task is done successfully. Otherwise, it's 0.
Which mimics the real-world sparse rewards, but it's delivered reliably inside this synthetic world.
Then that synthetic data feeds into the second pillar, the experience replay buffer. This starts off seeded with some offline data, maybe a small public data set. But the crucial part is that it's continuously enriched with fresh trajectories that the agent itself is generating.
So the buffer is co-evolving with the agent. As the agent gets better, the synthetic experiences get better.
That's it. It ensures the synthetic rollouts are always aligned with the agent's current policy, which leads to much more stable training. And they tested this. They did an ablation study where they removed the reasoning step.
And what happened?
It really hurt the informativeness of the states it generated, and it caused a big increase in hallucinations. It just confirms how vital that chain of thought step is for quality.
So the synthetic world has to keep getting harder as the agent gets smarter. Which brings us to the third, and I think maybe the most elegant pillar, the curriculum task generator.
This component is actively making up new tasks. It creates variations of existing ones, and it shares parameters with MEXP. But the really smart part is how it chooses which tasks to work on.
It uses a metric they call group-based reward entropy.
It does.
Here's where it gets really interesting. The system deliberately looks for tasks of intermediate difficulty.
You can think of reward entropy as a teacher looking at test scores. A high entropy, or a lot of variance, means the agent is getting a mix of successes and failures on that task.
Okay, so if the agent always succeeds, the reward is always 1, the task is too easy, no new information there.
And if it always fails, the reward is always 0, the task is too hard, and the agent can't learn anything useful.
But that middle ground is where the learning happens.
That intermediate entropy is the sweet spot. It means the task is possible, but it's challenging. The agent is forced to learn the subtleties. That's where you get the most information for credit assignment. The agent learns from its mistakes and its near misses. So the generator is constantly pushing the agent toward these harder, more valuable problems.
And the ablation study for this component showed just how necessary it is. When they removed the task generator, the success rate just plummeted.
It dropped by about 6.6% in WebShop and 6.0% in WebArena. And that happens because without the generator creating a new curriculum, the replay buffer just fills up with the same easy, repetitive stuff.
Exploration stalls.
It stalls completely. So that component is absolutely vital for pushing the agent to keep learning.
So these three pillars create this incredibly efficient training loop. But the real test is in the results. Let's look at the numbers across the three benchmarks: WebShop, ALF World, and WebArena.
The findings are really compelling, especially on WebArena, which is a good example of a non-RL ready task. Like scalable infrastructure, reliable resets.
Mm.
It's a mess.
And DreamGym.
DreamGym was the only viable RL training approach. It got success rates over 30% higher than all the baselines. This proves it can make RL feasible in domains that were basically considered impossible before.
So it unlocks RL for places we just couldn't use it before. What about the environments where it was possible, but just way too expensive?
On those RL-ready tasks, like Web Shop and ALF World, they saw a massive resource saving. Agents trained purely synthetically so, with zero real-world interactions during the RL phase, they performed just as well as traditional methods.
And those traditional methods were using what? Tens of thousands of real interactions?
With up to 80,000 real-world interactions.
Mm.
And you have to think about what that means. 80,000 steps on a complex website could be a huge amount of money in cloud compute or API calls. DreamGem just replaces that cost with structured computation.
That's a huge difference.
But the most striking result came from their sim-to-real transfer test, what they call DreamGem S2R. The idea was to train the policy mostly in the synthetic DreamGem world and then transfer to the real environment for just a little bit of fine-tuning.
And that gave them a performance boost.
A more than 40% performance improvement compared to training from scratch in the real world. And it did that while using less than 10% of the real-world data, just 5,000 steps.
Wow. That really puts the efficiency gains in perspective. The paper says it reduces the total training effort on WebArena to, what, a third or a fifth of what other methods require?
It does. And that efficiency comes directly from that dense, curriculum-based feedback and the lightweight, abstract state transitions we talked about earlier.
And that abstraction leads to better generalization.
It leads to a really powerful generalization. Policies trained in DreamGym could successfully transfer between completely different web domains, from Web Shop to WebArena and back again. They often performed better than models that were fine-tuned directly on the target domain's data.
So the agents aren't just memorizing how to do one task.
No, it suggests they're learning domain-agnostic behavioral priors inside that abstract space. They're learning how to reason about actions and consequences, no matter what the specific user interface looks like.
So the overall conclusion from the research is pretty clear.
It is. The biggest bottleneck for applying RL to these big LLM agents isn't the agent model itself. It's the quality and structure of the interaction data. DreamGym seems to solve that by generating these scalable, reasoning-driven synthetic experiences.
So what does this all mean for you? Well, if you're involved in developing or deploying these kinds of general-purpose language agents, DreamGym offers a really powerful, scalable, warm start strategy. It's a way to build sophisticated agents without that huge upfront investment in gathering thousands and thousands of real-world interactions.
It dramatically lowers the barrier to entry.
It does. However, the research does point out some important limits we should think about. The abstract representation worked beautifully across similar domains like different websites, but when the domain gap got too big...
Right, when they tried transferring a policy from a web environment to an embodied control task like ALF World, performance dropped quite a bit.
Which highlights that while this is a huge step forward for bridging related domain, creating a truly universal world model one that can go from web navigation to, say, controlling a robot, that remains a very open and very difficult challenge.